Okay, let's begin. So today's agenda is to finish what we started last time, closest pair, the closest pair problem, and this will complete our study of divide and conquer. And then we will talk about, so I would say we'll probably take the first quarter of our class on this, maybe first third of our class on this, and then the remaining time we will spend on covering some elementary data structures, and you might have seen variants of it. You certainly implicitly use it all the time if you're writing any program and invoking many of the data structures such as hash maps and things like that. So we will review these. We will go into a little bit of detail, but not too much, but we'll try to encapsulate what we learned into certain facts that we will repeatedly use later. Okay, and then after this we will start a component on graphs, and we'll talk a lot about graph algorithms. So then we move on to greedy algorithms, dynamic programming, and so on. Okay. Logistics, PS3 is out, and it is due next Thursday. We have a midterm on Friday, and that midterm is not in class. Done, 6 to 7. So actually keep 6 to 8 p.m. available, and we'll post the location and time to. I'll talk a little bit more about the midterm once more students. Okay. So let's talk about the closest pair problem and what we covered last time so far. So remember, the closest pair problem, what we were looking at was closest pair in 2 dimensions. You are given n points, x1, y1, x2, y2, xn, yn. You're given these endpoints, and your goal is to find out 2 points that are closest in their Euclidean distance among all the n squared possible pairs. We observe that if you do brute force, you need to check n choose 2 equals n times n minus 1 over 2 squared. So this is a theta n square time algorithm. And our question was, can we do better than this? Okay. So we came up with an algorithm. The idea of the algorithm was we are given a whole bunch of points in this plane. We will identify a dividing line such that half of the points are on this side and half of the points are on this side. Okay? And we can always find it, just the median line. You can sort all the points according to their x coordinates. You don't need to sort. You can just find the median of all the x coordinates. That will give you this line. So you have a bunch of points here and a bunch of points here. Okay? So that is our first step. So let me write down the algorithm here. So closest pair, and let's say you're given a set S of n points. What do we do first? And I'm going to write down here in sort of pseudocode, but without too much notation, but it's very clear what the output is. So closest pair of S is find median of the nx coordinates. Find median x and x star. Find median x star of the x coordinates. Set f out the points on the left to be set of points with x less than equal to xl, and the right hand side is set of points with x greater than. Okay? By the way, when I write like something like this, what I mean is we are partitioning. So this corresponds to a walk through all the points, a scan through all the points, and putting some points on one array and other points on another array. Okay, that's what this means. How will you write this in code? You write for I equals 1 to n. If xi is less than or equal to x star, you put it in array L. If it's greater than s star, you put it in array SR. Okay? Okay, good. Then what did we do after this? So we split the points into two parts, and then we found the closest pair on the left and found the closest pair on the right. So that's a recursive call. So let's suppose we have to use some notation. Let's say P L1 L2 is closest pair. Let me actually write it differently. So we're returning the coordinates. So there are 2 points returned in the closest pair for SL. These 2 points, how do we return the points? Let's say what we return is the x coordinate and the y coordinate of those 2 points. So we have to return 2 pairs. One pair is, let's call this xl1, y1, and the other pair is okay. So on the left hand side, these 2 points are the closest pair. Let delta 1 be the distance between these 2. So delta 1 is the distance between x1 and y1. Okay. I'm assuming there is a distance function that takes xy coordinates of one point, x2 coordinates of the other point, and returns us the distance. And what is that? That's simply the square root of the sum of the squares. Okay. Similarly, we have to do the same thing for x1. So x1 r, y1 r, closest pair r, and delta 2 equals this of x1 r, y1 r, x2 r. Okay? What did we do after that? Well, the next thing we observed was we don't need to work, so now we have to do the cross pairs. We have done everything on the left-hand side, we have done everything on the right-hand side, now we have to look at all the cross pairs. So if you have to look at all the cross pairs, we can't afford to look at every cross pair. So we focus our attention on those cross pairs that could possibly be that could possibly do better than this. Okay? So we said let delta be the minimum of these two. Okay? Then we said we are going to take a region to the left of the line delta over 2, delta over 2, region to the right of the line delta over 2, delta over 2. Okay? So this is delta over 2, delta over 2, delta over 2. And then we also split this into these blocks. Okay? Now you'll notice that this is for our analysis, but let's try to see how we go about doing it. Then we observe that no cell is occupied by more than 1 point. The number of points in a cell is at most 1. And finally we observe that if you look at any point, the only possible candidates that it could do, that could possibly be such that its distance is less than delta, there are basically 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 10 other cells that could possibly be there. Okay? Okay, so, any questions? Yes?
I understand how you did the vertical line,
yeah.
But how did you define, how did you know how the distance between the horizontal lines?
Okay, so good question. So, in this picture, the vertical lines, every distance is delta over 2. Every cell's distance is delta over 2. Okay? Notice that I'm not writing these steps down there because we are not going to actually divide the space into delta over 2. Okay, why are we not going to do that? Because the points themselves might be really spread out. And if I keep doing this delta over 2, I'm spending a lot of time just, imagine this delta might be really, really small. And I'm building these cells. Most of these cells are empty. So I can't afford to do that. Now my time might depend upon the distances as opposed to the number of points. Right? Because for example, imagine there were 2 points here that were really, really close. Okay? So my delta over 2 is really small, and I'm taking this whole space and dividing into these really fine cells, which are vast majority of them are completely empty. Okay? So, but this drawing is for our reasoning, which will lead to what you will do. Okay? So the reasoning why we were looking at delta over 2 and delta over 2 was simply because of the fact that, remember, our distances have to be the only interesting distances are less than delta. So if you have something in a cell here, then we immediately can rule out things like this, right? Because this is delta over 2 up and delta over 2 away. So we basically are left with, did I do it correctly? Something like that, maybe not that one, that one. So for each point we identified at most 10 other cells. So for this point, for example, we said the only possibility is in this region. Okay? Is that clear? So how many points do we have to compare this point with? At most 10. Okay? You agree? Yes?
Sorry if I missed this, but is line 6 supposed to be by R? Oh, it's not a crossing there, right?
Closest.
No,
Thank you.
Yeah. Okay, thanks.
Yeah, no, thanks. This is closest. This is not a crosscut. Okay? So for this point, we need to compare it with at most 10 other cells. Okay? All right. So how do we implement this? Is the question. So what we could do. So any thoughts on? So it's clear to you, everybody, where we are going. So we have all these points. We can restrict our. How do we restrict our attention to points here? Yeah.
So you already sorted them on the x-axis. I mean.
I have not sorted them yet, but we could if you want.
Oh, okay. Then you can sort the left within the delta area, and then the parts on the first half of that area you can sort for the 5 corresponding ones on the right of the median, and then on the second portion on the left side you test the 10 points on the right side of the median.
Okay, so let's see.
Or you just simplify and do the 10 different.
How do we? So let's do it slowly. So let's focus our attention on. Let's say we want to only look at the points here.
Yeah.
Okay. So I'm going to write down the rest of the algorithm on this side. Okay. So how do we restrict our attention to only points in this region? We don't want to know. All I want is right now. You're not going to tessellate because tessellating the cell is too expensive. Okay. I want to find out all the points that are in this space. Yeah.
Just find the x's that are less than x median by a delta and greater.
Okay. So you can just do a linear scan on all the points and only include those points whose x coordinate is between the median minus delta and median plus delta. Is that clear?
You have to see with respect to y also, right? What if
No, right now all I'm asking is how do I want to compare. So I want to compare. I'm only looking at points in this area, and points in this area are completely determined by their x values. Okay, so let's start that. So I already found the median. Okay, so let me say, let's call this set T. Find this and I'm just going to write down T equals. Okay, you have to figure out the way we are finding this is by just doing a linear scan over all the points. So T equals set of points in S such that whose x coordinate is in the region x star minus delta and x star. Okay? And I'm writing that, but it's clear to you how we are doing it. We are doing it, how long does it take to do this? Linear time. We are simply doing it's a for loop. For I equals 1 to n, if xi is less than equal to, if xi is greater than equal to x star minus delta and less than equal to x star plus delta, put it in T. Okay? So more and more as we do algorithms, we are not going to write down longer statements. We will assume that from this you should be able to write this as a for loop and write it in a piece of code if you want. Okay? Is that clear? Any questions for us? Good. So far I have restricted to this. Okay. So now let's do the next one. I want to, essentially what I want to do is I want to find every point in this region and compare it with the 10 points that could possibly be closer to within that. How do I do that? Is the question clear? I found out, I now have a list of all the points in the space, except they are right now. I could sort them. It was suggested that I could sort them by x coordinate. I could do whatever. I could do something to them. But my question is, how do we take this set T? And now I want to walk through every point in T. And for every point, I only want to compare with the possibly 10 points that could be candidates. I cannot afford to compare this point with everybody else, because we know that there could be there could be a lot of points here, right? There could be all the points. I mean, this area and this area could be empty. All the points could be in this region. You have no idea. So I cannot afford to compare with everything. Let's take somebody who has not spoken. Yes.
Could you find the x that's closest to x's that are closest to said median point, and then start testing the y?
Okay. Well, how do you test the y? So let's say let me pick this particular point. Okay. And by the way, I should do this for every point, even for points that are farther away. I have to do this for every point. Okay. So let me just take this point. Okay. You want to compare its. What do you want to do? So you want to compare its y with other y's.
Yeah, and I want to kind of keep kind of a cost.
Okay.
Keep the distance if I could.
Yeah. You can calculate the distance for anybody by just making one call. Okay. But how do you do? So what do you do for this point? The question is, how do you find out these 10 points?
I thought we found it with regards to finding the set of points.
The 10 points, these 4 points I've drawn here are sitting in the set T.
Okay.
But how do I pick those 4 points? They're all sitting in the set T, but this point is also there, this is also there, this is also there, this is also there, and so on.
We need the y within that set then.
You do have the y. What do you do with those y's?
Grab them.
Well, but then if you grab all of them, then you have all of the y's.
Can we just grab just the x and y from that?
Yeah, you can get all the y's.
But I just want that set. Could I just say?
No, you have all the y's in the set. You have the entire set T.
Okay.
You don't have the set right now. That's what you have to find. So, what you have is the x and y for every point you see here. And from this, I want to only look at those points that are there in this box. And the question is, how do I do that fast? Okay? Yes?
You do another for loop and you test all the points.
Yeah.
If the y value is the y value of that particular plus or minus delta,
Good?
and the x value is the median
Good.
minus
Okay.
delta.
Well, that's all good. Very good. Okay, that's a good suggestion. So what I could do is, once I take this point, I could do a check through all the points in T and pick only those points which are on this side. Okay. By the way, I could have split this into T1 and T2 if I wanted, right? Since I already had split them into S1 and S2, I could have done T1 is set of points in S1, T2 is set of points in S2. I could have done that, so that I have separated them into 2 sides. Okay. Then what I could do is, for this point, I could go through all the points on the left side, in T, and only pick those points which are less than equal to delta away from this in its y coordinate. Is that clear? Okay. You have a comment? Yes.
If you're doing that for every single point, that's n square cost.
That's the problem. If we do this for every single point, for every point here, I do a scan of the entire T, that's the same thing as the number of points in T times the number of points in T, so that's the number of points in T squared. And as I said, in the worst case, all the points could be sitting inside T.
So you have to find only one closest pair. So if even there's 1, 2 points which are closest.
Well, it may take you to the very end to find that.
Yeah.
So it could still take you as much as n squared. Okay? Yes?
Could you order all the points so that when you do this many times, you already have all the values?
Very good. So one thing we could do is order all the points according to the y-axis, the y coordinate. Okay? That's a possibility. Let's do that. Sort T by y coordinate. Now, how do we really efficiently use it? I've sorted all the points. I think I could do it. I've sorted all of them together, so I've lost this T1, T2. Okay, don't worry about it. But I've sorted all the points. Okay, so now what do I do?
You can find out the delta in y and just do a binary search to find out in that y sorted by coordinate to get the distances that come in.
So how do I do that? I mean, I give you all the y values, so you have all the y values available to you.
And using that one on the right hand side, for that y value, you see what's
Okay, good. Okay, for that y value, okay, that's a good suggestion. So, so then you have that. So now you have this point. We know what its value is, and then so let me draw the picture so that so you have all the y values written down. So the y values could be 95, 92, 9, 8, and now you have a point sitting here. Let's say our point has a y value of 80 or something like that. Then if delta is, let's say, 0.5 or let's say 2, then I look at all the points that are between 82 and, so 80 plus delta and 80 minus delta. I search for all the points. I search for 80 plus delta, I get this. I search for 80 minus delta, I get this. And I look at all of these points. Those are the only points that could possibly be candidates. Okay? And I know that there are only 10 on this side. At most 10 on this side that could satisfy that, probably even fewer. Okay? There is one issue that some points from here will also show up. But that's okay. If I just compare with them, it doesn't matter. I'm just doing a little bit of wasteful work, but it doesn't matter. Okay? So that's an algorithm, potential algorithm. I've sorted T by y coordinate, and then for each point I search for 80 plus delta, and I search for 80 minus delta, and then I compare with only those points that are there. Okay? Just once again. An easier way to do the same thing is, you have sorted all the points by their y coordinate. Look at a particular point sitting here. Okay, its y coordinate is sitting here, and that y coordinate was 80. Okay? We know that if you look at it sitting somewhere here, okay, there are at most 10 cells on this side that could possibly be candidates. Okay? And then there are, let's say, 10 cells on this side. Any point below this and above this I need not consider at all. So if I look at only the points that are, let's say the 10 points on one side and 10 points on the other side, and I only compare with them, I would have taken care of all of these points. Okay? So what I'm going to do is for each point whose y coordinate is sitting there, and actually to be just more careful, I will probably do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 points on one side and 12 points on the other side. For each point, I will compare with 12 points on this side, 12 points on this side, and check what their distance is, and I'll note down the minimum. Okay, so let me write it out. I'll write this out more carefully so that it's clear to you. So for all points P in T, okay, calculate, say dP is the minimum distance P So for every P, I will calculate the minimum distance of the point P from the 12 points whose Y values are immediately higher than these, and 12 points whose Y values are immediately lower. Okay? Yes?
I was just curious, in the step 10, why do you sort? Why not just do a similar thing that we did in 9, where we also have a condition of the range?
Well, the reason is we'll have to do this for every single point separately, because the range is different for each point, right? For this point, my range is this plus delta or 2 delta, whatever it is, this plus delta, this plus delta, that's my range. For this point, it's this plus delta, this plus delta. So I will have to, there are other ways to do it, but at least the way if you're going to look at this, if you're going to look at all these points, we look at this, then we pick the 10 points. Then we look at this, then we look at another 10 points. Okay? So if you're doing this repeatedly, going through all the points, then it's going to take us a linear time again and again and again and again. Okay? We are trying to avoid that by doing this. Sorry. Okay. Yes?
Sorry, it's a little hard to read what that says.
Okay, I'll read it out. Yes.
Yeah.
So for every point in T, dP, I'm defining something, some variable. This is the minimum distance between P and the 12 points whose Y coordinate is immediately higher than P, and the 12 points whose Y coordinate is immediately lower. Okay. Why did I pick 12? Is because if I look at this point, the points that could be immediately higher are something here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Actually, I only need to do it for 11. And the ones that could be lower are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So you can replace that 10, 12 by 11. Okay? We are not going to bother about these constants because we are finally going to just get an asymptotic form. Yes?
We don't need to compare the points on the same side.
You're right. You don't need to compare with the points, but since I sorted the entire T, I'm not distinguishing between the points on the right and the points on the left. You're absolutely right. You don't need to compare. So the other way to do it would be to keep T1 separate, T2 separate, but then you are trying to sort on both sides, and we are looking for this comparing with points on the other side, so it's a little bit more painful to do that. You can do it if you want. When you're doing this comparison, you could say, I'm only going to look at points on this side. That's also fine. You could do that. Okay. There is no harm, of course, on re-comparing with this, because we are always going to pick the minimum, so it doesn't count. That was one. Any other? Any other questions? Okay. Okay, so then what do we do? For every point P, we have figured out this. Then what do we do? So for every point P, we have found its candidate closest pair. Pardon? You can compare it
From a medium.
So we have delta, and we have dP. Then we find the minimum among all the dPs, and whichever is, and compare it with delta, whichever is the champion wins. Okay. Of course, when I say a minimum distance, I should also keep track of the particular point that is giving me the minimum distance. So you'll have to write down that piece of code as well. But I think people should get the idea. So 11, I'm going to just finish that up here. So return that minimizes delta 1, delta 2, and dp. Okay, this is again a little bit cryptic sentence, but I think people should understand what's going on. Delta 1 was the pair returned here. Delta 2 was the pair returned in the second call. dP over all P returned the best pair for every point, and we are going to take the best among all of this. Okay? And we are going to return a pair of points, right? Point? Yes.
Isn't delta the
Minimum. Yes, so delta was the smaller of delta 1 and delta 2.
So do you need delta 1 and delta 2?
Well, you could have written delta instead of this. This is fine. The only reason I wrote delta 1 and delta 2 is because we are also delta 1. If it is delta 1, then we have to return these two. Right?
Okay.
These 2 points. If it's delta 2, then you have to return these 2 points. Okay. But if you only have to return the distance, then I could just say minimum. Okay, so if you, let's say our problem was just to find the minimum distance, not the actual points. In reality, most of the time you're interested in the points in addition to the distance. But if our question was just return the minimum distance, then I could have simply written return minimum of delta 1, delta 2, and the minimum of all delta p. I could just write the number. But here I really want to keep track of which points are going to do it, right? Okay, is that clear? All right, so just recap what we did. So we first divided into 2 parts, the divide step. And how did we divide it into 2 parts? Using the median. So we used our selection algorithm. Then we split this into 2 parts, found the closest pair on the left side, found the closest pair on the right side. Then we took the, on both of the distances and took the minimum of those distances. Then we concentrated our attention on the portion around the median line that could possibly be corresponding to this closest pairs. And notice that in this picture I have tessellated into delta over 2 cross delta over 2 boxes, but the whole purpose of this calculation, of this tessellation, was to tell you that for each point you only need to look at 20 other points or 10 other points on each side. That's all there is. Okay? So this tessellation is only for our analysis. We never actually go ahead and construct these subsets. Yes?
Instead of using delta, use delta over 2?
Where?
Restrict the number of comparisons?
Yeah. So notice that the only even here. So notice that in the code, delta only appears here. After that, only what we have is this 12.
No, I mean like when you find the minimum distance to the left, to the median, to the right. That's the original delta, right? Why do we need to look at the entire range? It can't be if you divide things delta over 2 on each side.
Yeah.
Nothing can be.
No. The reason is look at this point here, and this point here.
Oh, okay.
Right? So, yeah. And by the way, I must say that these numbers that I'm writing here, these are not the best possible. You could do a more careful analysis and get a better number. We are just being conservative because we want to make sure that we get the minimum for sure. Okay? Okay. And as it turns out, whether we replace the 12 by a 10 or an 8 or a 9, the impact on the asymptotic running time in our theta notation won't matter. Of course, in practice it will matter. So in practice, if you have to code this up, you don't want to look at the same points that we looked at before. Why do we want to look at the range? Okay, so you want to do this very carefully, but I think those details will take a lot more time to figure out. So we're not going to. Okay, so the algorithm is clear. So is this really doing anything better than n squared? So our comparison is n squared. Okay? Okay, so let's figure that out. So let's try to analyze the running time. So at this point, we should be able to quickly translate an algorithm like that into a recurrence relation. Okay? Why is it a recurrence relation? Because there is a recursive call. Okay? All right. So recall, let's say T of n is running time on problem of size n. on endpoints. Okay, so let's just quickly do that. Step 1. How long does step 1 take? And I'm going to ignore the constant in front. We're just going to focus the impact of n. What's the running time for step 1? N, linear. Okay, we have done linear time median selection. So that's n. Step 2. We are partitioning all the points into 2 parts, SL and SR. So steps 2 and 3, linear. Okay, step 4. Step 4 is the recursive call to how many points? Half the number of points. So T of n over 2. Step 5. Same thing. Sorry, step 5 is 1. Sorry, step 5 is 1. Okay, that's better. So 3 is n over 2. Step 5, 1. Step 6, 3 of n over 2. Step 7, 1. Step 8, 1. Step 9. Step 9 is I went through all the points, put them, half of them on one side, half of them, sorry, not half of them. I put all those points that are in this middle region. So that's n. Step 10, sort. Whenever I do sort, I will try to use the best algorithm I could possibly can. And the best sorting algorithm takes n log n time, so it's n log n. Step 11. So for each point, I am looking at the 20 points on this side and the 12 points on this side and 12 points on this side. So that's just a walk through the array. And for each point, I look at 12 points on this side, 12 points on this side. So for each point, I'm looking at 20 points. So it's basically 20 times n. Okay, or 24 times n. Okay? So that's n. Step 12. I'm comparing delta 1, delta 2, and for every point I'm picking the minimum. I'm picking the minimum over all p, so that's also linear. Okay. I could have, well, when I was doing this p, I could have kept track of the minimum also. There were many ways to do it. But. Okay. Clear? Everybody happy with that? Okay, so what's the recurrence from this? T of n equals, how many recursive calls do we have? 2. We have a bunch of n's and an n log n, right? And then a constant. So sum n, so theta of n log n plus n plus 1. Okay, I'm writing this little formally at the moment. What is the dominant function here? N log n. Okay, and so the recurrence for this is exactly the same. If you don't care about the constant, it's exactly the same as this. These two have the same behavior. Okay, so if I just extract out the most dominant function from there, that's my recurrence. Now this is the recurrence we have not seen before. At least in class we have not seen before. And what could you try to use for this? So you could try to use the master theorem. You could try to use the recursion tree approach. You could try to guess and prove by induction. Now, if you use the master theorem, you would, let's try to quickly use the master theorem and see what happens. What is f of n in the master theorem? N log n. What is a and b? 2. So what is n to the log base b of a? That is just n. So as we have studied, as the version of the master theorem we have studied, turns out won't apply to this. Okay, I think there was a Piazza post about something like this at some point. The reason is the way master theorem that we have looked at applies is it compares these two functions. If they are the same asymptotically, then it's just this whatever it is times log n compared to the number of levels. If this is much more than this, then this dominates. If this is much more than this, then this dominates. Right? So it's some. But the definition of much more is that it should be bigger than the other by at least an n to the epsilon factor. If you remember the definition, there is an n to the epsilon. It turns out that this is the Fn is bigger than this, but it doesn't dominate as much. So Fn is omega n to the log base p of a, but Fn is not omega n to the log base p of a plus epsilon. It's not. That's not true. So just applying the master theorem will not work. Okay, so the safest way, as in most cases, is to try to see whether we can do it using recursion. Okay, or the recursion tree approach. So let's do that. Now, okay, so let's try to see. So I just want to, I'll do it relatively fast. You should all be able to do it now. Running out for occurrences. At least build the tree. So what do I put here? N log n. And then I have T of n over 2, T of n over 2. Okay. I think it will be good for all of you to try to work this out on your own, if possible, and then try to match with what I'm doing here. Okay. What do we write for T of n over 2? N by 2 log of n by 2. And here n by 2 log of n by 2. And then T of n over 4, T of n over 4, T of n over 4. Let's open this one more level. What's the next one? N by 4 log of, and you have 4 of these, right? Okay, and then it keeps on going. Okay, so the contribution of the first level is n log n. The contribution of the second level is what? N by 2. So n by 2 times 2, that's 2. And log of n over 2. Okay? What's the contribution of the next level? N times log of. What do you think at the next level you will have? N times log of. That's a very nice, very clean pattern, right? Everybody sees that pattern. Good. And we know the height of the tree. What's the height of the tree? Log of n, because it's dividing by 2 every time. Now this one does look like something we have seen, but it's not. And why is that? It is decreasing. You agree that everything is decreasing. But it is not decreasing by a constant factor. Notice that this is being divided by 2, so that's a constant factor, but it's within the log. It's not, if this was here, then it would be fine. But it's within the log. Okay. Is that clear? But this has actually a very easy, fairly easy, straightforward calculation, as we will complete this now. So you have n, so n is everywhere. Okay. So let's keep going. In the last level, Okay? Actually, let me not. So I want to write down here n times, what's the first term? Log n. What's the second term? Log of n by 2. Can you simplify that? It's log of n minus log of 2. So it's log of n minus 1. So this is very important. Log of n by 2 is log of n minus 1. What's the next term? Log of n minus 2. And the next one, log of n minus 3. And there are only log n such terms, so it basically goes on all the way down to 1. Now this is nothing but the sum of conjugated numbers. What is the sum of m conjugated numbers? It's m times n plus 1 by 2. So this whole quantity is n times log of n plus 1 times log of n by 2. Okay? And that is nothing but, if we write the theta notation, it's nothing but n times log of n squared. Okay? Because this is log of n squared plus log of n, but log of n squared dominates log of n. So this is basically. Okay? So is this better than n squared? Definitely. Because we have replaced 1n by log of n whole square. And any powering of log, like log is much slower growing function than n. So replacing n by log of n square, log of n cubed, log of n to the power of 10, in principle, it's much better to do that. Is this better than n log n, just purely sorting? And for sorting, it doesn't solve our problem. But is this as efficient as sorting? No, because we have added another log n. Okay? Yes?
How did you get the numbers in the sequence there? The log n plus log n.
Okay, so this is this log n.
Right.
This is a rewrite of this.
Oh.
Log of n over 2 is log n minus log 2.
Oh, okay.
Log of a over b is log of a minus log of b. And log of 2 is 1.
Right.
That's
Okay.
what it is. So that's that. This is log of n times 2. Okay? Alright. Good. Very clear? So it turns out that this algorithm actually is n log n, even though our calculation is perfectly correct. And there is the algorithm itself as stated is not n log n, but there is only a small change you have to make it n log n. The change is, let's see what is going on in our algorithm. So we have written this recurrence down. So we are doing this 2t n over 2 plus this. So what is the dominant term here? N log n. So what is the dominant action other than the recursive calls? The sort. Okay? So just think about this recursively, what is going on. We have split this into two parts. We sorted all the endpoints. We only need to sort the ones in T, but we said that everything could be in T, and we sorted all the endpoints. Now we do the recursive call. On the half we do this, on the half we do this. We sort that again. And on right hand side half, we sort that again. But that seems we are doing this possibly the same sort again and again and again and again. So how do I avoid it? Go ahead.
No, I mean, maybe we can sort at the first time.
Right. So you sort at the very beginning. After that, you don't do the sort again. Okay? So I'm not going to make any changes to this code, but just imagine taking the sort out and putting it before we make any recursive calls. So you assume that in the closest pair, you're given all the points so that they're already sorted in the y-axis, for example. So they're already sorted to you. So that's an n log n, but everything else was just n. then the recurrence in the remaining quotient would be just T of n equals 2Tn over 2 plus theta n. That's exactly like in Mozart. And that will be okay. You have to be just a little careful on how you put this together in your code. I would refer to you to the book to go over it more carefully. But just to close everything up, basically closure pair in 2 dimensions can be done in chaos and logic. It doesn't take any more time than sorting, ignoring constants. Okay? Good. Okay. So let's move to so that basically completes our study of divide and conquer. We will be coming up with divide and conquer kind of algorithms as we go along, but we are going to study more different kinds of paradigms as we go along. But before we study other paradigms, it is important to just review some elementary data structures that I've said that you use them implicitly again and again. And so we are going to talk about hash tables, binary search trees, heaps, and priority queues. Before I introduce any of them, I'll just do a simple one example question, and then we will go with that. Okay. So before I talk about that, since we have a reasonably full house, let me remind you that we have the first midterm next Friday. Okay. The exact location will be posted, and the exact time will be posted, but basically it's in this period, 3 p.m. The material covered in the midterm would be everything until what we do today. And if I do any review in the next couple of classes, of course, that's included. But the portion, we are going to start a portion on the next component we are going to start, the next module is going to be on graphs. That is not going to be included. Let me make a few more comments. There will be a review for the midterm. We will most likely use the recitations, the one or more of the recitations as a review for the exam. We will post review problems. Think of those problems as practice problems. I mean, it's very difficult to craft out problems very similar to the exam. So think of those as practice problems. In general, the problems for a midterm would be easier than the problems you see on a problem set, because these are limited time problems, and sort of similar difficulty to what you saw in the quiz. That's all. I'm happy to take questions.
Yeah, I was going to ask if the problem set 3 will prepare us for the midterm, but it sounds like it's past the midterm scope.
Now the problem set 3 is due on Thursday.
Right.
So,
will doing it?
Yes, absolutely.
Okay.
Yeah, so the problem set 3 is on divide and conquer, and it's basically a review of something you must have already studied for problem set 2, for example. So, and we will post the solutions immediately after the deadline of the problem.
So there is material be covered in the event today?
Yes. Yes. Potentially, yes. Any other? Yes.
I'm assuming no like formula sheets or.
We haven't decided on that, but certainly closed book. I can imagine. I don't know. We haven't decided on that. We'll get back to you pretty soon. Yes.
Do we have to like memorize the master theorem, or will that be like provided somewhere?
It's a good question. It won't be provided.
But the cheat sheet should be provided. Should be allowed.
So if a cheat sheet is allowed, then you can put it in. Any other questions? Okay. All right. So let's do one problem. Okay, so let me give you a problem. It's a problem, a fairly straightforward problem. So I would like all of you to try this right now. like a quiz problem, okay, an exam problem. So let's say I give you the following. I give you n integers, n numbers. So in a list, in an unsorted list, in an unsorted array A, and I also give you a number, an integer, let's call them so n integers in an unsorted array A, and then I also give you an integer k, and I ask you the following: find x and y belonging to A such that x plus y equals k. Okay? If they exist, if there is no such x and y, you should say no. Alright. I'll give you 5 minutes or a few minutes to think about how you go about solving it. As always, we want to look at you want to make sure that the algorithm works correctly, and you want to do as well as you can possibly do in its running time as a function of n. Is the problem clear? You have n numbers, n integers. They are given in an array, so that's the input. And you're also given one number k, and you're asked, are there two numbers in this list which add up to k? If you find no such number, you should do that. Okay? You have 5 minutes to work on it. You can talk to your neighbors. You have a question? Not necessarily. These are just integers, positive, negative, 0.
If you find one such thing, is it enough?
It's enough. Just find, if you find one such thing, that's enough. Just return it.
For the k minus x. If it's sorted,
assume there are no duplicates if it helps you.
Do we have the space, the time,
Pardon?
do we have the space, the time?
Well, give the best space and best time you can possibly use. It's possible, yeah. So if you have two different algorithms, different space, different time, then maybe it'll work.
that would be n squared.
I think as always, it's important to make sure whatever algorithm you give is correct, it works perfectly, even if it's not the most efficient. But then try to give the most efficient.
In the problem,
You have a question? Yeah.
in the problem set that you asked us to, you guys have an algorithm. But that also should exprove the correctness.
So if it, we will, I think in by default in every problem set, try to prove the correctness, try to analyze and so on. In an exam, it will be very clear when you have to prove anything because you have limited amount of time. But in general, in something like this, if you give an algorithm, it will be fairly obvious whether it is correct or not. But you don't have to make obvious statements, but certainly justifying why your algorithm works. All right. So everybody has time to think about this. Okay. So let's try to think about some algorithms for this. Any suggestions? Who wants to give their? Yeah. Go ahead.
So you can do one pass for all the elements in the hash map set.
Okay.
So you have like a 1 x.
Okay.
And then you can iterate through the, so if you have say element x,
Yeah.
and you see it came out as y in the hash map.
Okay. Good. So here is the algorithm. Put elements. Put the n integers. Hash map. And then what do you check for? Check. Then you iterate through for every x. Check k minus x. Okay? There was one algorithm given. Any other algorithms you want to suggest? Yeah.
You do like a divide and conquer game.
Okay.
Break it into half and half.
Okay.
Keep going it until there are 2 elements.
Okay.
And then if the sum is equal to
K. Yeah.
return.
Okay. So let's say we take this side. So break it into 2 parts. Here you check whether the sum is, you do a recursion here, you do a recursion here. But remember, then you also have to check whether 2 elements here. You also have to check the cross. You have to also check the cross pair. And the number of different pairs to check in principle is as many as n over 2 squared, similar to what we did. So this, if you were to fix it by checking for every pair, this will end up taking quadratic time. And certainly quadratic time is possible. What do you do with quadratic time? Well, look at all pairs and see whether they add up to k. Okay. So let me call that brute force. You check all pairs, that's clearly theta n squared. Time, space-wise, you're not using any more space than the array. Okay. That's clear. This one we will analyze later, but do people have some other suggestions? Or any other algorithm that people want to suggest? Okay.
So we split the whole set into 2 parts,
okay,
where on the right side everything is greater than k, and I'll subtract k from it. And if I check that if the same answer exists on the left side, then I have found a pair. Else, what I'll do is, on the other half, I'll again recurse the same algorithm.
So you want to take all the points,
but this time instead of k, I'll take k by 2 on the left.
So you're taking all the points less than k put on one side, all the points greater than k put on the other side. So the problem is there will be nothing on the other side. It's possible. So then all the points might be just on one side.
Yeah, then I'll go by k by 2 and split it again, and I'll check.
Okay. And then what do you do once you check? So here this is, let's say, less than k, and here this is greater than k.
So I'll subtract k from the right side, and I'll check if the same element exists on the left side.
How do you check whether this element exists on this side? Do a linear scan for, but for a lot of points, right? You're going to do it for every point. So that might be n by 2 times n by 2. Possibly. I think that might end up taking somebody else. Yes?
Yeah, so another way that's not as fast as the hash map one is you can sort the array and then finally check for every element for k minus x.
Okay. Yeah.
I think this is the same thing as the first one, but you could iterate through the array and create a second array and use the number, the integer in the first array as an index in the second, and if basically you mark the number as present in the second array, and then you could pretty much check it.
Okay, good. All right, I think we pretty much have all the ideas in place. So let me note down the sorting algorithm. So the algorithm said sort the array A. So now it has all the elements in sorted order. Now you do a binary search for k minus for each x. So for each x and A, binary search to see if k minus x okay. Let's try to understand the running time of this. What is the sorting running time? N log n. The number of iterations of this is n. Each iteration takes log n. So this is theta and log. So it clearly beats the brute force. Okay. Now let's look at this hash map, which is a little bit similar to what is also mentioned there. So the thing about the hash map is, of course, we are using some data structure. We are not sort of using it as a black box. So let's try to understand what is going on in this black box. So a hash map, as the name suggests, and there are different kinds of uses of hash map, but at least in this case, as the name suggests, this is the data structure that allows you to maintain a set of elements and answer queries such as, is something in there? Okay? And what it uses is, as you would expect, it uses a hash table. Okay? A hash table has lots of nice properties. What it would have is the nice property that, in fact, the running time of this on expectation would be linear. We will review that. But in the really unfortunate, very sad worst case, it could be as much as n squared. Okay? So if you were really looking for a truly deterministic algorithm, which will work regardless of whatever happens, this is the best we would know how to do it. Sorting and then looking for response. But for the vast majority of practical scenarios, this is the algorithm we will deploy. And certainly, randomized algorithms work very well in practice. So let's try to understand this as the basis of hashing. Okay, so the idea is that the idea is fairly so you're trying to maintain a dynamic set, and the operations you're allowed is insert, delete, and search. Okay? So you insert some quantity, you can insert any element, you can delete any element from the set, and you can check whether an element belongs to it. Okay? One way to do that, there are multiple ways to do it. One way to do that is what is called a binary search tree. We're not going to go into details on it, and it essentially operates sort of in some sense similar to what's going on there, but it's a more versatile and generic data structure. In general, what it does is I'll give you an example. So what it does is it maintains all the elements that you're given in a certain order, and the order is basically that it maintains that in a binary tree. Let's say all the leaves store all the elements. And the leaves are stored in a sorted order. Sorry, the numbers cannot be clear, but basically they are in sorted order. And numbers here designate sort of comparison points where you will tell which side you have to go. So for example, this number might be the smallest of this, so 25. Everything greater than or equal to 25 goes here, so if it's greater than or equal to you go here, if it's less than you go here. This would be 28. Sometimes you allow binary search tree. Internal nodes can also have keys and things like that. So this is a binary search tree. It allows you to store all the elements in a certain way, so that if you're adding something to this, we will basically know where to add. If you're subtracting something from it, if you're looking for something, you can search and see whether you reach a key with that value. If you're removing something, then you can go to that point and remove it. But one main thing is you want to keep your binary search tree balanced. Because once, if you start removing all the elements here, and then you're starting adding all the elements here, and you keep growing the tree, then the running time becomes pretty large. So there are standard data structures for managing heights of binary search trees. We are not going to go over binary search trees, but the idea is what a binary search tree allows you is to maintain a dynamic set in which in search, and delete, everything can be done in order log n time. All of them can be done in order log n time, where n is the number of elements in the dynamic set at any point of time. Okay, where does log n come from? It comes from the height of the tree. Okay, so but of course you have to keep the tree completely balanced. So you have if the tree is very skewed, then the height of the tree is no longer order log. So it's not easy to maintain the balance, but there are many ways to do it. Okay. Hash table. So by the way, one other thing that, as you can imagine, binary tree search trees are very good at is answering questions as, okay, what is the next highest element? Okay, so if I look at this, what is the next highest element over 19? That can be done very fast in a binary search. You can find the successor of that by going up and then going. So what is the successor of 20? So you can keep going up until you take a right turn, and then you keep going for the leftmost one. So it can answer a lot of other things. It can answer successor, predecessor, print things in sorted order. You can do a walkthrough. All of those things can be done very well. Okay. Yes?
That question you said the immediate successor, wouldn't it just be the right node 20?
It is so. It is the next key in this last level. Yes.
Yeah.
Except that what you're storing is only your parent and your sibling, or maybe your sibling. But you're basically only storing your parent and your children.
Yeah.
So how do you go from 20 to 25?
But what do you know that's underneath? What's the child underneath 20?
There is no child underneath 20.
Oh, okay.
20 is a key.
I thought those were bad children.
No. So 20, sorry, I should have drawn bigger. But 20 is a key here. And I want to find its successor. So I basically keep going up the parent chain until I make a right, and then I basically go to the other side and then go all the way left. There is a specific, it's easy to see what rule you follow. Okay, it's not that. So you can do a lot of things with boundary search trees. You can look up insert, you can search, you can delete, and so on. But let's say you're in this problem we were looking at, didn't care about the ordering of the numbers. We didn't really care. All we cared was something that adds up to something else. Okay? So the ordering, even though we did that only so that we could find things fast. Let's say we're only interested in doing insert, delete, and search. I don't care about ordering. Okay? So this is exactly where a hash table works better. A hash table will allow you to do insert, delete, and search in expected table. What does expected mean? So we know this is expectation of random variables, a basic probability. So expected is if the expectation of a variable is, just to review, expectation of a random variable is I consider all possibilities that the random variable can take a certain value and multiply by that value over all possible choices of A. So expectation of variable x is A times the probability that x is. So when I say expected theta 1 means on average it will basically take constant time. Sometimes it could take a longer time, but most of the time it will actually end up taking. It turns out that this becomes so the bigger implication is that if you consider m insert delete search operations, if I consider the sequence of search, delete, and insert operations, each time it's going to take constant time, right? Expected. Sometimes it could take more, sometimes it could take less. But when I add them up, I'm basically going to get theta m. Right? Now the probability of this deviating from theta m becoming much more than theta m is very unlikely. So you would end up saying, oh, if you have m insert, delete, search operations, it's theta m with high probability. So it's not just expectation, it's actually theta m with high probability. Very good probability this actually theta m. The longer and longer your sequence is, the much more likely it is very close to the expectation. Okay? Okay, so let's review what hash tables actually do. So, how do hash tables work? So the way hash tables work is literally, as the name suggests, you have some kind of a table in which you store things. So what we will have, let's say in our example, we had n elements, right? So what we will do is, let's say we would have a table of size n. This is just an array of size n. Okay? And m, typically you would make it bigger than the set that you want to store. Okay? And usually you don't want to make it much bigger. So it's a little bit bigger than your typical n, but usually you would say between n and 2n. Okay? Okay, that's your table. Now, what are you going to do? When you're trying to store x, you will say, okay, I'm going to store x in a particular location. When you're given a different x, you will store it in a different location. Try to. You're given a different x, you'll store it in a different location. Then, when you want to find out whether x is in there, you will look up x and somehow figure out exactly where to look for it, and then retrieve this there. Okay? Good. So this function that you apply to determine where you're looking for is what's called the hash function. So h is a hash function that takes a particular domain, in this case the domain of numbers or whatever you want to think of. Let's say it's called the universe, and maps it to 1 through n. That's the job of the hash function. It's going to take x, give a single number between 1 and n, and plunk x into that. Okay? So far, so good? Then you agree that insert, delete, and search are actually very trivial. What does insert mean? Given x, what does insert x do? Insert x means store x in location edge of x. So in the, let's call the table as T. So it's just an array. Store. This is it. Okay. What does delete? What does search x mean? Essentially, return whatever you see in T of hx. If it's empty, then the x is not there. If it's not empty, then it's maybe there. So now I'm keeping this a little bit loose at the moment, but we will solidify this. Delete x is also similar. If you find it there, then remove it. So notice that, at least the way I've written it, the only interesting thing going on is the calculation of h of x. And then just look up, right? So, of course, there are two problems. One is the calculation of h of x. I haven't told you what h is, how complicated it is to calculate. The second is, there is no guarantee, meaning the universe that I'm trying to map. So let's say I tell you that I have n numbers, right? I just tell you there are n numbers. So I build this table, and let's say n is, let's say, 1,000. So you choose your n between 1,000 and 2,000. So let's say you choose something like 1,000. So I have 1,000 numbers. So my table is of size 1,000. But my x, I didn't tell you what the universe is. Somebody asked me, is this negative integers at all? Yes, sure. It could be any integer. Okay. So these numbers could be drawn from a range of minus billion to a billion. So two different x's could be mapping to the same place. In fact, you know for sure that if I'm trying to put a billion numbers into an area of 1,000, there will be a million points that will go to the same place. So both of these statements are not precise. So what does it mean when I say store x and t h of x? What if there is something else already there? What do I do with that? So there are standard answers to this. What do you do when you're storing x into t of h of x? If something else is already there? Well, just add it as a linked list to the end. So what the table looks like is this, but in reality, it's just pointing to a linked list. Some of these are empty. Okay? So now, what does it mean for store of x and t of h of x? Put x as an entry in the linked list. Clear? What does it mean to say search of x? What do you do? Search in the linked list. So when you say return t of hx, you don't return t of hx. You search for x in the linked list t of h of x, and if you find it, return. Okay? Clear? What about delete? If you delete a particular x, you first search for it, go into the linked list, and then you delete. If you're trying to do deletions and insertions in the linked list, it's sometimes helpful to have the linked list as a doubly linked list. So that's easier to take things out and connect things together. So in general, these will look like this. Probably doesn't matter, but okay. So far, so good, right? Okay, so now let's try to understand what the running time of these operations are. So, what is the running time for insert, search, and delete? First is the calculation of the hash function. Okay, and then after that, going through the linked list. So, what is going on? We will observe that we can actually come up with hash functions that take just as much time as doing some computations on x. So that's actually doesn't take much time. So the time is dominated by the size of the linked list. So the running time is essentially theta of size of linked list. The size of a linked list in a hash table, of course, depends on our luck, right? You could have a number of, if all the vertices, all the points were such that they were all ending at the same location, then the linked list would be large. This is what is called collision. So whenever you hear the term hash collisions in a hash function, it basically refers to, okay, what is the likelihood of the size being quite large. It also sometimes addresses the collision in hash function. So what we can see is the following, and this is the first claim we're going to make. So if you have to minimize collision, what would you do? If you want to make sure that you don't have the luxury to go through all the points and put one in each place. That you don't have luxury. But whenever you have x coming in, you want to be able to decide where to place it. Yes?
Maybe you make the size of table M the root of the total size of numbers.
You could make M to be your entire universe. Right? Excellent. But then even after that you have to do something. Then you just store x in this location, which is equal to the value of the number. The problem with that is your table is just massive. Okay, you are completely giving up on space. You only needed to store 1,000 numbers, but I told you that these numbers could be anywhere between a billion or a trillion and a trillion. Now you're building a table of size trillion. The vast majority of those entries would be empty. Yeah.
I mean to say, you find like the root of the size of the universe, so the square root of it. Make that
square root of the size of the universe. Of the size, well, even then, I'm not sure.
Then the linked list would be about the same size as the size of the table.
So the universe, the thing is, the universe actually in some sense could be vastly, vastly much bigger than n. So that would could be still a bad idea. But okay, any other thoughts? Yeah.
So can we modify the h function?
You can do it whatever you want.
And make the h function to output the unique result for every element in universe.
For that to be able to do that, you have to know what's being stored right now. So every time a new element comes in, you should look up what is there in the table and then pick something to put there. The problem is that that your h function is now not dependent on x alone, it's also dependent on what's there in the set. So it's not really a function of x, it's a function of x and the table, and the current situation of the table. So when you look for x again, you won't even know what h function to use, for example, where you store. Okay, that's an important thing. You want your h to always return the same thing for a given x, otherwise it won't be very useful to come later. Yes?
Basically, I have the same idea as him, but right now I have another idea.
Yeah.
So maybe when we found a collision, then we can find, then we can go to the next empty spot.
Okay, so we could, when you find a collision, we could move it to the next empty spot. That would certainly remove the collision. Except when I next search for it, I still have to figure out, maybe it was a collision, that's why I moved to the next point. So what's happening is that the linked list is not here, but it's sort of getting added elsewhere. Okay?
We can have a strategy to have some report for that.
Yeah, there are ways around it, but I think it fundamentally does not avoid the collision. If you define the collision as what happens when I try to apply the hash function, I get the same thing. That is okay, so I'll just, I think we're running out of time, so I'll just say one point. So the idea behind a hash function is, what we would ideally like to do is map things completely randomly. Okay? So put every thing x in a random position. If you put everything in a random position, the expected number of collisions we will show is just constant. Okay? So on expectation, basically the size of these tables would be very small. 1, 2, and so on. There were two issues. One is sometimes it won't be the case. But the second issue is, how do I said randomly, but then I want to be able to calculate it again and again, and I can't keep doing this randomly. So we'll figure out, there are hash functions that work almost as random. And those are the ones that are used in hash maps. Okay. We'll stop here. We'll go at the beginning.